Well, great. Now that we have an understanding of what regression is and how a regression model works, I guess we should see how we can build one in Azure Machine Learning. So Steve, why don't you talk us through that?
Sure. So on my screen here, I've built a regression model in Azure Machine Learning. Now, in a previous demo, Graham showed you this data set, which is the exercise data. So we have these characteristics from each participant, and we have the labels in terms of calories for their exercise sessions, and you join those data. And so the first bit of my experiment here, which is typical of any machine learning experiment in Azure Machine Learning or any environment, is I'm going to do some data prep. I'm going to get it ready so that it's in a form that I can model. So the first thing I want to do here is I'm using this edit metadata model, and we have this one column called gender, and I'm going to make that a categorical variable because it really is. It's male or female, so there's only two possible categories there. Next, if you recall when you saw the graphs in Graham's demo, there were some curvy-looking relationships in some of those scatter plots. And so to deal with that kind of curvature, to kind of flatten it out, we're going to try doing what's called some feature engineering here. And for two features, duration and heart rate, we're going to include a new set of variables that is the square. You see, I've got the power function for two of those variables. Now there's a special situation here with this particular problem that calories have to be positive numbers. You can't have negative calories. There's no such thing. So I'm going to log transform calories, which is my original label, using this other apply math operations module. And I have to always normalize numeric values when I'm doing any kind of machine learning, and it's supervised or unsupervised. And what normalization I use depends on the distribution of those data. So I have some of these data that when you looked at the histograms in that scatter plot matrix Graham showed you, you may have noticed some of them look kind of like bell-shaped curves, normal distribution. So we'll use what's called a z-score normalization, which is mean variance normalization that works really well for variables like that. But we had these other variables like age, duration, and of course duration now squared, which had just distributions that are strange in some way. So we're going to use a simple method called min-max normalization for them. So it simply puts the values in a range 0 to 1. And there's just one last piece of data cleaning I need to do here, or data prep, which is I have these two columns that I don't want to confound the training of my machine learning model. User ID. So obviously a user ID is just something we assign to our participants, has no value in terms of predicting, and we don't want to use the original calories because we're going to use log calories as our label. So I'm setting those, I use this thing called clear feature, so they're no longer used in the regression model. So now we're down to actually building the machine learning model. So there's this kind of recipe we follow for any kind of supervised machine learning in Azure Machine Learning, and a lot of other environments too. But in this case, we're splitting the data, and we're going to split the data in this case so that 70% is used to train a model and 30% we're going to use to score and evaluate that model. And you always want to do those as random, independent splits, so you're not getting false good values of your model performance because you don't want to be evaluating on the data you use to train the model. You want some other set of data. So we split, and then obviously we've defined a train model module. And notice there's only one parameter we set there, which is what the label is that we're trying to predict, which is the log of calories. And we need to say, well, what model are we training? So in this case, I've put this linear regression module here, and I've connected it up, to the trained model module. And you can see I'll set some parameters here. Not so important what those are, but that's so this module defines my type of machine learning model I use, and it lets me set the parameters for it. So now I've set up to train a model, I've split the data so I can score the model, so I use the results of my trained model and this 30% in this case of data we didn't use to train the model, I get scores. Now my evaluate model module computes various metrics for the regression. We talked about those metrics when we went through the animations. We'll see some actual examples here now. And finally, because we computed log of calories as our label, I'm going to transform that back to actual calories with the exponential function. So let me just run this whole thing for you, and we'll see what happens. Okay, the model is run. And as a first quick look, let's look at what score model module produced here. So I'll visualize that output. And I'm just going to scroll over here. So scored labels are the values our model predicted for those test data, those 30% of the data I held back. And ln calories is the known values of the label. And you can see they're pretty close in most cases here, right? See, if you go back and forth between those two columns, they're not too different. So that looks pretty promising. I can look at the evaluate model module output here. I can visualize that. So we talked about a number of these metrics already. So we have like mean absolute error and root mean square error. Now they're small numbers, but keep in mind we are dealing with not the actual label, but its log. So those are on a log scale. So they need to be fairly small. More useful in a case like this where we've transformed the label to something that isn't the natural units that we can think about are these relative absolute error and relative squared error. And you can see like relative absolute error is around 14%, and the relative squared error is not even 3%. So this is pretty good. And this coefficient of determination, recall I said it's on a scale of 0 to 1, where 1 would be a perfect fit. Basically, you've overfit or overlearned the model. So we're at 0.97, which is, again, pretty good. And finally, we can look at this histogram of the residuals. And we see there's a few outliers, but they're generally clumped in this pretty small range over here. So that's all quite nice, just what we want. And finally, we can look at the untransformed label. Let me scroll over here. So here we've got this. In this last column, this is in units of calories now, and I'll call your attention to calories over here. So we've got 14 compared to 14, a little bit of an error, 51 compared to 40, but then 39 compared to about 41, et cetera. So again, it confirms that our model has fit both the log label and the actual label in units of calories rather well. And so I think we're at a good point here.